In the previous video, we talked about rates of change as one application of derivatives. And those are very useful in a lot of the more scientific types of uses of these ideas. But of course, this is a business calculus class, so let's look at some applications in the realm of economics. Hopefully you're pretty familiar with the concept of cost, revenue, and profit, but what we're going to do here is treat each of these as a function of the number of units produced or sold. So let's go ahead and give letters to these. We're actually going to use x here. This is going to be the number of units. Whether or not that is produced or sold, it will be up to the application. We're going to have a function c of x. So the cost, the total cost of those x units. We're going to have r of x. This is the total revenue. Of those x units, probably from selling those x units. And p of x is going to be our profit, our total profit. Now, of course, these three variables are not actually completely independent of each other. The profit is, in fact, the revenue minus the costs. Hopefully that's pretty clear of an idea. I don't know how much economics everybody's had so far, but I mean the amount of profit should be how much you get from selling those units minus how much you had to spend on making or obtaining those units. Now, of course, x here is usually going to be an integer. It doesn't make sense to say sell half a car, but frequently, especially in calculus, it makes it a lot easier to work with these functions if we can let x be a real number. That means we'll assume that everything works out kind of smoothly between those integers. In fact, in able to use any sort of calculus for these problems, we're going to have to do that. Calculus doesn't work when a function only works for integers. And so we might have to round our answers to the nearest sensible values at the end. But it'll work out overall. When we're working with these functions, we have another name for our derivatives. The derivative of the costs, this is referred to as the marginal costs. The derivative of the revenue is the marginal revenue. And big surprise, the derivative of the profit is the marginal profit. So you can just think of marginal here as just meaning derivative. But that's just the term that's used in economics. What these marginals do is they indicate how much our function changes if we change x. Basically, you can think of it as if we produce or sell one more unit, then our cost should change by the marginal cost, our revenue should change by the marginal revenue, and the total profit should change by the marginal profit. This will make more sense if we go through an example. Just like in the last video, I'm taking an example from a previous edition of the book. So this is not actually, this particular one is not in the book. Though just like the first one that we did in the last video as well, is actually very similar to one that is in the book. It actually looks very similar to the 32 that is in the book. But the other one that we're going to do later on in this video will be very different. But we have a formula for our revenue. So this is a function of x. If you have a particular number of apartments that we're renting, then our function giving us the revenue for those apartments is given by this formula. We're wanting to find how much additional revenue we get by changing the number of rentals. Basically, for part A, we need to know what is the revenue if we have 14 rentals, and what is the revenue when we have 15, and how much did we change going from 14 to 15? Well, we're following this formula, so we go ahead and plug in 14. And of course, I'm going to use a calculator here. I'm not going to try to do this by hand. And I get 32,256. Of course, notice here that the revenue is in dollars. So we plug in X, which represents apartments, so number of apartments, and we get out dollars at the end. We do the same thing with 15. Do basically the exact same formula, but we have 15s instead of 14s. This time I got 34,650. Still in dollars. And so the additional revenue we got from renting 15 apartments versus 14 is just going to be the difference between these. 34,650 minus 32,256, and we get $2,394. That's the additional revenue. In part B, we want the marginal revenue when x equals 14. Remember, the marginal revenue here, we're talking about the derivative. Of course, differentiating this directly as it sits is actually a little bit tricky. We don't have a way to do products yet. That's actually our next section. But because we can actually just distribute the 2x each term, let's just go ahead and do that. So r of x is really 1800x plus 64x squared minus 2x cubed. And notice I just put an additional x on each term, and I multiply each term by 2. The derivative of this, well, the derivative of 1800x, well, I have 1800 times the derivative of x, which is 1. Then we have 64 times the derivative of x squared, which is 2x. And minus 2 times the derivative of x cubed. This one we actually haven't done since last section. So remember that we just have a power of x, so we take that power, we bring it down in front, and then we reduce the power of 3 to a 2. We reduce it by 1. We go ahead and simplify that out. This is just 1800. We have a 64 times 2, so we have 128 times x. And then finally we have a minus 2 times 3, which is a minus 6. And we solve the x squared. So this is our formula for our marginal revenue. Of course, they want it specifically the marginal revenue when x equals 14. So go ahead and plug 14 into this function. And of course, we're going to go ahead and use a calculator here just to save us the work. And the answer I got was 2,416. Now here, this is in dollars. So marginal revenue is just like a change in revenue in that we just get units of dollars. Now, when we worked with rates of change, we usually got whatever units we were dealing with over time, over seconds or over hours. Because we're just working with units here, you could say this is actually dollars per unit. That would be another way of looking at it, but it just depends on exactly how you want to write it. I guess that's probably what we should say here. $2,416 per unit. Now, part C, we want to compare these two results. And we can see that they're not too far off. In fact, they're only about $22 off. And that comes into what we mean by these marginal what we mean by marginal revenue. Essentially, when we're talking about the marginal revenue at 14, what this is saying is that if we change this 14, we change this x value by 1, we should change our revenue by this amount. Now, of course, we saw here that we didn't get exactly this amount. We got something that's rather close. But if you compare the size of these numbers here, we're talking about a $2,000 difference overall, and our estimate, if we use our marginal revenue as our estimate, was only off by $22. So if we're willing to ignore that $22 error, we can actually use this value here as a good estimate for what we should expect if we were already renting 14 apartments and we were wondering how much more revenue would we get if we were renting 15 instead. How much more revenue would we have if we went out and tried to get someone else to rent an apartment from us? And if we don't need the exact amount, we can at least estimate that we should get about $2,400 more dollars. And that's what this is all good for. It gives us a way of estimating how much things would change if we made certain changes to our business. If we change our business in one way, how might it affect our revenue or costs or profit, whichever value we're looking at the time. And this gives us a way to say, well, yeah, if we rent another apartment, this is about how much money we should get more. Even if it doesn't give us the exact amount, it might still be a very useful thing to get. Now, of course, we don't always expect to just be given the revenue function. They gave us the revenue function in that example. In the real world, we usually have to come up with something on our own. So we're going to look at how we might do that. Now, we've already actually seen one formula for dealing with that. We already saw that profit equals revenue minus cost. So if we have the revenue and cost, we can get the profit. What we want to look at right now is how do we find R and how do we find C? And we're going to deal with those slightly separately. So the cost here. Now keep in mind that the process of finding these formulas can be more complicated when what we're about to do. This is kind of just a starting point. In a very simplified example. But when it comes to cost, usually what we'll have are two different types. We'll have a fixed cost. This might represent the cost of the building or the machines that you're using to create items or create whatever units you're dealing with. It might have to do with, say, the cost of your employees, any sort of things like that. Now, of course, maybe making more units might require you to hire more employees and stuff like that. We're not really taking that into account right now. There's a lot of variables that can come into play. But in the very simplified version that we're looking at right here, we're just going to assume that we have some fixed cost, whatever it is. Then we also have a variable cost. This depends on X, of course. It varies over X, and this probably represents the materials that are used to create whatever units we're talking about. So to produce 2 pizzas takes twice as many materials as it did to produce 1 pizza. So a simple model for cost might be something like C is equal to the fixed cost plus the variable cost times X. Okay? That's not too bad. What about revenue? Now, revenue is actually pretty simple first, but there is a slight complication here. First thing we note is that if we have a price P, so P is going to be our price, then the revenue will just be given by X times P. So the number of units sold times the price that they're sold at. Multiply those together and you get the total amount of money that you got from selling the items. The problem here is, of course, that we have two independent variables. We have X and we have P. We want this to only depend on one variable. So in order to do that, somehow we have to get rid of P. And we're going to do that by what we call a demand function. This is going to be some formula, P equals f of x. This is some formula that tells us the number of units X that customers are willing to purchase when the price is set to equal P. Now, this may look kind of backwards, that you might want to think of X as a function of P instead of P as a function of X. But it's actually going to be more useful for what we're doing here, because we want things to be put in terms of X to write it this way. But in general, this would be something that we could solve for either P or X. It'll be some equation that we can solve for one or the other. And so this is just a more useful way of writing it. If we write it that way, then our revenue function will look like X times f of X. In this course, we're not going to get too into what possibilities there are for demand functions. You'll either be given the demand function, or it'll be assumed to be linear. So if it's linear, we'd have something like P equals mx plus b, and we'd have to find out what m and b are given some information. Let's look at this in an example, and it'll make a lot more sense. This is 41 from an old version. It's actually very similar to problem 40 in the book, though the numbers are definitely different. But we're talking about a baseball game. We're selling tickets to the baseball game. When we set the price of the tickets to $6, we notice that we sold 36,000 tickets. When we set the price of the tickets to $7, we notice that we sold 33,000 tickets. We're going to assume that we have a linear demand function and that we have variable and fixed costs for our ballpark that are given by the fixed cost is going to be $85,000 and the variable cost is basically 20 cents. We want to find a formula for the profit, meaning that we're going to take all the information that's given there, turn it into a cost function and a revenue function, and then combine those to make a profit function. And then we're going to solve some problems based off of that. Or we'll at least discuss what the properties of that profit function. So, let's start with the costs. So our cost here, our fixed cost, remember, was $85,000. Our variable cost is 0.2. I'm going to leave that in the dollars and not convert that to 20 cents now. And that variable cost is going to be multiplied by X. X here representing our number of tickets. So the cost function is actually not too hard to get. It's the revenue that's going to be a little bit trickier. Remember, the revenue is going to be X times P, but we need to find out what P actually is here. They're assuming here that our demand function is linear, so it's going to look like P equals mx plus b. And the point here is that this formula has to be satisfied by these 2 points. We have 6, 36,000, and we have 7, 33,000. Remember here, P is the price, so that's the 6 and the 7, and the X is the 36,000 and the 33,000. So our M, our slope, we can actually compute that using our slope formula. But keep in mind which variable is doing what. On top, we need a difference in P values. On the bottom, we need the difference in X values. So that means on top, I'm going to take 7 minus 6. On the bottom, I need to take 33,000 minus 36,000. Of course, the top just comes to 1. The bottom, we actually have a negative 3,000. I'm going to go ahead and put the negative out in front, though. So we have a slope of negative 1 over 3,000. Kind of a small number there. But that's what you might expect in a lot of applications. I'm just going to go ahead and leave that as a fraction. I'm not going to try to put that into decimals because it'll actually be helpful in the long run. I do need to find out what my b value is. And to do that, I'm just going to go ahead and use one of my points. I'm going to go ahead and use the 6 and 36,000, and I'm going to plug those into my formula. Basically, a price of 6 equals our slope of negative 1 over 3,000 times the x value, which is 36,000, and then plus b. And now I'm going to solve for b, because everything else is replaced with numbers. If I solve for b, basically I'm going to take 6, and I'm going to add 36,000 divided by 3,000. That actually comes out fairly nice. We get a b of 18. And so our demand function is p equals, I'm going to go ahead, because this is negative, I'm going to put it in the back. I'm going to put b plus mx instead. So we have 18 minus x divided by 3,000. That's my demand function. So my revenue function, r, is going to be x times that. Basically, I'm going to multiply both these terms by x. We have an 18x, and we have a minus x squared over 3,000. Of course, our profit function is the difference between these. It's r minus c. So I'm going to take my formula for c and my formula for r, and I'm going to subtract them. Of course, r is the only one that has a quadratic term in it. C only had only a linear term and a constant term. So we'll have a minus x squared over 3,000. Then we have a linear term in both these. We have an 18x and we have a minus 0.2x. Why did I make that minus? That should have been plus. Sorry if that confused you before. That should be a plus 0.2x. I'm actually going to be subtracting it now because of the minus sign here, though. So we'll have 18 minus 0.2. That's going to give me a plus 17.8x. Then finally, I'm still subtracting c, so I'm going to be subtracting this fixed cost as well. So this is my formula for my profit. That's all part A. Using a graphing utility to graph P, so we're going to be graphing this function. And we're going to talk about the slopes when x equals 18,000, when x equals 36,000. So we go ahead and just put in our function. So P of x is equal to minus x squared over 3,000 plus 17.8x minus 85,000. And we don't see anything. Well, we probably shouldn't expect to see anything, because keep in mind what these axes are actually showing us. The bottom axis is showing us the values of x, and our x value is the number of tickets. Our tickets here are in thousands. We should expect to see that from 0 to 28. So one thing that we can do in GeoGebra is essentially just grab our axis. As long as we select the move graphics view, we can grab our axis and move it to actually rescale stuff. So I'm going to rescale this until we can see 36,000 on here. Actually, let's leave it there. Now, of course, this zips right off the graph, because our vertical axis, this is the amount of profit that we have. Our profit, we expect to have at least, we want to have more than $17. So let's shrink that down until we can actually see what's going on. There we go. That's a lot better. So we're looking at profits in the terms of really hundreds of thousands. But this is a graph of our profit function. Of course, they want us to look at what's happening to the slope of this graph when x is 18,000 and when x is 36,000. I'll go ahead and actually show on here x equals 18,000. So there we can see where that actually hits our profit function. So our profit here looks like it should be somewhere between 120,000 to 130,000. On the other hand, if we look at x equals 36,000, now we get a point over here. This is actually somewhat similar, actually. But what we can see here is the slope of our graph. Over here, if we look at a tangent line, it's going to have a positive slope to it. Over here, if we have a tangent line, it's going to have a negative slope to it. And that will actually tell us a lot about what kind of situation we're really in. Now let's go ahead and actually find what those slopes should be. Because they're asking us in part C to find the marginal profits. So we're going to take this formula here, we're going to differentiate it, and we're going to plug in the numbers that they're asking for. So let's give ourselves a little bit more room. Here's the formula from the last page. We're going to differentiate this, which we can write as P prime, or the book is wanting us to write dp dx, but they're just different notations for the same thing. We want to differentiate this. So here we have an x squared, but multiplied by negative 1 over 3,000. So we take that negative 1 over 3,000, and we multiply it to the derivative of x squared. We know that derivative is 2x. Next we take the 17.8 times the derivative of x, which is a 1. And finally, we have a constant at the end. Derivatives of constants are just 0. So really the only simplification to do here is we can cancel a 2 with a 2 from the 3,000. That turns the 3,000 into a 1,500. And so this is our formula for marginal profit. If we look at the values that they're wanting us to plug in here, so first they wanted us to plug in 18,000. So negative 18,000 divided by 1,500 plus 17.8. Again, use a calculator, get 5.8. If we instead plug in 36,000, we have minus 36,000 divided by 1,500, still plus 17.8. And this time I got a negative 6.2. So what do these numbers mean? Notice that by our formula, when we sell 18,000 tickets, if we go back to our profit, we have a profit of 100,027. Okay. Let me actually just write this down. So P of 18,000 is 127,400. There. In fact, we can actually go ahead and use GeoGebra to find that for us. So P of 18,000. Why did you take off the 1,000? Oh, it's turning a comma into a decimal point, essentially. There we go. So that's the number we were expecting. We can actually look at the point 18,000. There we go. That represents this point up here. That has an actual y value of 127,400. What our marginal profit there is telling us is that if we sell one more item, if we sell one more ticket, because these represent tickets in this example, then we expect our profit to change by $5.80. So P of 18001 should equal that plus 5.8. Well, if we actually go ahead and do that, P of 18001, and then click this button to give us an approximation rather than this fraction, we actually get exactly what we had. We have 127,405.8. Now, GeoGebra is actually doing a little bit of rounding here. It's actually like 0.799 or something like that. So we're not getting the exact answer here, but it is a very good estimate. If we look at the other side and look at 36,000, then our marginal profit of negative 6.2 means that if we increase the number of tickets sold now, our profit decreases by $6.20. Or if you look at another way, we could say if we sell one ticket less, then our profit actually increases by $6.20, approximately. In other words, if we're looking at our profit here and asking ourselves whether we should sell more tickets or fewer tickets, this is giving us an indication. When we're selling 18,000 tickets, we should probably sell more. Our profit went up if we sold more tickets. Whereas if we were selling 36,000 tickets, then selling more tickets actually decreases our profit, whereas selling fewer tickets increases our profit. So we should sell fewer tickets and we get more money overall, at least in terms of profit. In fact, optimally, we would want to be up here at the top. If we're at the top of our curve, then changing the number of tickets sold one way or the other is just going to decrease the amount of profit. That means they have the most profit we possibly can have. Of course, finding the top might be a little tricky. We'd have to go through a few things to try to find this top point. And that's actually one of the applications we're going to see later on in Chapter 3, using calculus to find what we call the maximum or minimum of a function. In this case, we'd be maximizing our profit function. And we'll find a very nice way of tackling this issue, and be able to find exactly what this top point is. If you want to know in the particular for this example, it actually turns out that we want to sell 26,700 tickets. And I put the wrong number in there. That should be a 6. There we go. That gives me my maximum point up there. And which, finding that 26,700 may not be so obvious. But once we actually have the techniques of calculus, this one's actually not that hard to find. So I'm not going to go more into how you actually find that, but that's the idea behind all this stuff. That we can use calculus and able to solve these kind of problems pretty easily, in fact, as long as we know how to actually construct a function to work with. Alright, in the next section we're actually going to get into a few more rules. We'll talk about how to differentiate products and quotients, and that's will actually kind of be the rest of our week. We'll have another rule coming up in 2.5 as well, so I'll talk about that more when we get to it. But I just wanted you to know at this point what derivatives actually do for you, rather than just we look at a graph. Well, there are actually a lot of real-world applications of these concepts where we actually can solve problems using derivatives. So hopefully this section was helpful. I'll see you guys in the next video.